Welcome back, everyone, to another college algebra lecture. Today, we are going to continue on in Chapter 4 and begin our discussion about exponential functions. Now, exponential functions are very important in mathematics, and they show up all over the place. We will deal with them this section, plus for the couple more sections after this. All right, so to begin with, the definition of an exponential function, they are any function that takes on the form f of x equals c a to the x. Now, what's special right here is the location of your variable x. An exponential function, exponent, will have your variable located in the exponent. That's what's important. Now, as far as the c and the a go, they are both important to us. The a is what has the x or the exponent attached to it. So just be cautious that the x right here is only attached to the a. The a is referred to as the base. And the c, the one that does not have the exponent, that is called your initial value. Now, the reason we call this one the initial value is that if I were to start with, say, initial time t, or t equals 0, or 0 for the exponent, the a would wind up going away, and we just get c left over. So it's called the initial value because we start with 0, and the whole exponent part goes away. Now, as far as the base goes, the base can either be called a growth or a decay. The reason it's called that is if our base a is bigger than 0, or I should say it's bigger than 1, then you're going to be multiplying by that same number over and over and over again. Well, if you multiply by a number bigger than 1 each time, your function grows, it gets bigger. If you multiply by a number less than 1 that's positive, it's a small number times a small number gets smaller. So every time you multiply by a number bigger than 1, you're going to get bigger, growth. If you multiply by a number less than 1, you're going to get smaller, decay. All right, so to start with, all I wanted to do is figure out what your base, initial value, and growth or decay is for an exponential function. So looking at this one right here, my base a is equal to 7, because that is the one that has the exponent attached to it. The initial value, c, is 8. That's the one that does not have the exponent attached to it. Now, as far as whether this is a growth or decay, my base is bigger than 1. That means it is a growth. And again, the reason we call this a growth is every time I change this exponent, I'm multiplying by another 7. 7 times 7 is 49. That gets bigger. The more times you multiply by 7, the bigger it gets. Now, for the next one, my base a is 1 over 9. And my initial value c is 5. 1 over 9 had the exponent, 5 did not. Now right here, since 1 over 9 is a number that is less than 1, this one is a decay. We say it's a decay because every time I increase x, I'm multiplying by another 1 over 9. So 1 over 9 times 1 over 9 is 1 over 81. Sorry, blanked for a second there. So that's a smaller number. It's just going to get smaller and smaller and smaller. Okay, moving on. For c, my base a is 0.89. And the initial value is 4. Okay, now as far as whether this one's a growth or decay, this might be a decimal, but we know that this decimal right here is less than 1. So since that is less than 1, this is a decay. Problem solved. For the next one, our base a, that is 5 over 2, and the initial value is 100. Now I know it's very tempting to say, oh, it's a fraction, it's a decay. Be very careful. This fraction, that winds up simplifying to be 2.5. That is bigger than 1. So this is a growth. Got it. Now the next two will require you to think just for a second. So starting with our base a, well, the a is the one that has the variable. So that means a is 3. Now as far as the initial value goes, there's no number in front. This is where it pays to know the definition of initial value. The initial value is what we get whenever we plug in 0 right here. So 3 to the 0 is equal to 1. Another way to think about this, there is an invisible 1 that I'm multiplying by out front. All right, now for the last one. This one will require the most thinking out of all of them. It's very tempting to say that our base is 5. That's what we've been doing so far. But this -2 right here is important. So looking at just that, if I have 5 to the -2t, that's the same thing as saying 5 to the -2 to the t power. Well, we've learned before in previous classes that if you have a negative in the exponent, that just means you flip it over. If you don't remember, I'll cover it again a little bit later. And now I can see that this is 1 over 25. So looking at it this way, now that t is in the exponent by itself, my base is actually 125. And my initial value here is c. Knowing that, this one is a decay, and this one is a growth. So the only one that was a little tricky was this one right here. But when you're figuring out whether it's a growth or decay, you need to pay attention to the exponent. Don't say it's one or the other until the variable is by itself. Okay, so now we know what these look like in terms of functions, and we can figure out whether they're growth or decay based on the base. But I kind of want to take a moment and talk about where these come from in terms of a graph. It might make our life a little bit easier and help your understanding. So taking a look at our next one right here, I want us to build up to some properties. So in example 2, I tell you f of x is equal to 2x, or 2 to the x power, and g of x is equal to 1/2 to the x power. Now, based on the previous page, we know that this one is a growth and this one is a decay. But let's plot some points and see what that looks like in terms of a graph. All right, so starting with f of x right here, if I were to put -2 in for x, that would be 2 to the -2. That winds up giving me 1/4. If I were to put -1, that gives me 1/2. 0 is going to give me 1. 1 gives me 2. And 2 gives me 4. Now, at this point, I want to kind of tell you where these are coming from, because if you're in this class, you might not be sure yet how I'm getting these, apart from plugging it in the calculator. So just taking a brief moment to explain where this comes from. On the previous page, I said you keep multiplying by the same number. If I tell you x equals 1, substituting it in here, I have 2 to the first power, which is 2. If I do x equals 2, that gives me 2 to the second power. That's 2 times 2, which is 4. If I tell you x equals 3, 2 to the third, 2 times 2 times 2, that gives me 8. Every single time I go up in x, I am multiplying by yet another 2. So the base is the number that we multiply by each time. So if I want to do 4, I'd have 2 times 2 times 2 times 2, which would give me 16. So I get my next number by just multiplying the previous by 2. Now, going backwards, that is an exponent property, which I'll explain a little bit if you don't remember what it is. All right, so now that you know how you can get these even if you don't have a calculator, let's move on. So doing 1/2 to the x power, 1/2 to the negative 2 gives me 4, because the negative tells me I have to flip it over. And if I do negative 1, that gives me 2. 1/2 to the 0 power gives me 1. 1/2 to the first power gives me 1/2. And the 1/2 to the second power gives me 1/4. Got it. Okay, now that we have some points, we can actually go through and graph these. So starting with this one, I know I have the point 0, 1 right there. I also have the point 1, 2. So 1, 2 right here. I also have the 2, 4 point right here. And also I know based on what we just did, I also have 3, 8. Got it. All right, go into the other direction. I have 1/2. I have 1/4. Now at this point, before I start graphing it, I want to draw your attention to something. Based on what we said right here, we are multiplying by 2 every time. So if I'm going backwards, that's the same as multiplying the denominator by 2 every time, or dividing by 2. If I keep going by 2, I'll have 1/2, 4, 8, 16, 1/32. But I'm never going to get to 0 because I'm always multiplying by 2. That means whenever I draw this graph, I am going to make sure that I never cross or touch the x-axis, because I'm constantly multiplying by the number 2. That means I'm never multiplying by 0. That's my graph for that. Okay, so looking at this, I see reading from left to right, I start small and then I grow. So this is a growth, which makes sense because by definition, we knew it was going to be a growth. Okay, moving on to the next one, negative 2, 4. And I know I'll have negative 3, 8, just to give me an extra point to aim for. Negative 1, 2, 0, 1, 1, 1/2, 2, 1/4, and going on. And by the same logic, I'm never going to cross or touch the x-axis because I never equal 0. Okay, so graphing this. There we go. And now, reading from left to right, I see I start up here and then I decrease, I go down. That means that I'm getting smaller. It is a decay, which we knew that based on definition, but now we can see it graphically. All right, so now we know what these graphs look like. We're constantly multiplying by a number, and it's either going to go up or it will go down. Now, answering some properties based on this, can y ever equal 0? Based on what I said a few minutes ago, answer is no, it never will. Now, as far as y, here we know that you are always multiplying by 2 or 1/2, and that will never be 0. If you're constantly multiplying by 2, it's never going to get to 0 because it's always going to be times 2, times 2, times 2. Okay, next question. Do these functions have a horizontal asymptote? Well, we know that horizontal asymptotes are horizontal lines, ones that are go left to right, and asymptote means that it's something that my graph follows. So looking right now, I see that over on this side, my graph goes flat and follows a horizontal line. So the answer is yes. The line it follows is right here. And for the other one, yes again, it follows that same line, just on the other side. So they both have horizontal asymptotes. So yes, the horizontal asymptote is y equals 0. Is the line right here. Okay, so now we can keep going a little bit further. Domain and range. Well, we know that the domain deals with x values and the range deals with y values. Looking up here, I see that every single x matches up with a point on my graph. So -10, point right there. -4, there's a point right there. 0, there's a point right there. Even if I go all out here to 6, this graph is going to keep expanding out to the side. There would be a point. So every single x value shows up on my graph. So my domain here is -infinity to +infinity. But the range, however, is a little different. We know the range, those are the y values. Looking down here, if I'm on -10, -10 doesn't have a single point on my graph. -4, that doesn't show up anywhere on my graph. The first thing I see is right here above 0. If I go a little bit above 0, that shows up on my graph. 1 shows up on my graph. 4 shows up on my graph. 8 shows up on my graph. So everything above 0, but since I cannot equal, I am strictly above. So parentheses 0 to infinity. Ooh, can't see that. That's it. So that's the domain and range. Every single x works, but the range starts directly above 0. Now, as far as the x and y intercepts go, x-intercept, that's where we cross the x-axis. Well, we saw that that never happens. So there is none. For the y-intercept, that's where we cross the y-axis. I see that that happened right here at 0, 1, and right here at 0, 1 again. So 0, 1 is our x or y-intercept. Now, as far as the symmetry goes, we've dealt with symmetry quite a bit this semester. Symmetry, that's where we deal with either being symmetric with the y-axis, and that means an even function, or symmetry with the origin being an odd function. Well, I can't fold this over and it land on itself, so there's no symmetry with the y-axis. It's not even. And if I were to take this and turn it upside down, it would not look the exact same. So there is no symmetry with the origin. So right here, no. The functions are neither even nor odd. So there is no symmetry. But one thing that we can see is that they're one-to-one. No matter where I draw a line, because these are constantly getting a little bit smaller every time, I will never repeat. So right here, they are 1-to-1. That means that we can find an inverse. So inverses exist. That's important. And that's what we'll do next time. All right, so we just talked about a lot of properties just from looking at the graphs. And on this next page, I tell you exactly all those properties yet again. So right here, if you have a growth function, we know about the domain and range, we know the intercepts, we know asymptotes, we know increasing in 1-to-1, and we also saw some points that are always on there. So this is what increasing is going to look like. In decreasing, we have all the same properties, and we have an example of what it looks like. Now, what's important to see on here, for anything that's not transformed, we have 3 points that always show up. So that's the only special thing I want to show you on here. So right now we have -1, 1 over a, 0, 1, and 1, a, always are on the graph if it has not been transformed. That's important. So talking about the transformations, that's where we can either go side to side, move it up and down for shifting, stretch, shrink, reflect, all those fun things. If we don't do any of those, these points are guaranteed to be on there. And these two are super important. They always help out. All right, so speaking of transformations, let's talk about how we can use these points to help us graph functions that have been transformed. Okay, these next three problems, I give you an exponential that I want you to graph, and we're going to use transformations and the points we know to do them. So looking at this very first one right here, I give you f of x equals 3 to the x plus 2 power minus 4. Okay, well, taking a glance at this one, we know it's an exponential. Let's write down what the original non-transformed version would look like. So the original for this would be 3 to the x power. We know that because 3 is our base and it's exponential, so it would have x. This is a growth function. So we know it's going to swoop up. All right, well, for this, we know a couple points and a little bit extra. So a point we know that would be on the original would be 0, 1. Another point we would know is 1, comma a, where a is 3. The last thing, I know we have negative 1, comma 1 over a. That's not as important as this. We know that the horizontal asymptote is y equals 0. I could use all of these to help graph that really quickly. But this has been transformed. Let's figure out what transformations happen. So looking right here, I see that I have x plus 2. That's in the exponent. So this counts as a horizontal shift. So the horizontal shift, if I do plus, that means I go left. So I'm going left by 2. Now, going left and right, that deals with the x value. That'll help us out. Okay, now for the next one, minus 4 on the outside of the function, that means that we're going to go down by 4. And going down means we're going to change the y value. Now, how this combined with these points is going to help us is like this. Doing our transformations. I see that the x value goes left by 2. So if I'm at 0, go left 2. That gives me negative 2. Now for the y value, I'm going to go down 4. So down, if I start at 1, go down by 4, that gives me negative 3. This point has been transformed to that point. Now doing this again right here, I start with x equals 1. I'm going to go left by 2. That gives me negative 1. If I start at 3, if I go down 4, that gives me negative 1 again. Now for the horizontal asymptote, y equals, this is the line y equals 0. I'm going to go down 4. That's negative 4. I can use all this information right here to make my graph. So starting off, I'm going to put my y-intercept, or not my y-intercept, I'm sorry, my horizontal asymptote here at negative 4. So doing my horizontal asymptote, I have my dashed line. Now I can graph my points. I have negative 2, negative 3. So negative 2 and negative 3 right here. And then I have negative 1, negative 1 right there. And this is a growth, so I know I'm going to go flat right here. I'll start kind of curving up. I'll hit my point. I'll hit my point. Is it super accurate? No, but do we know a good bit of information about it? Yes. And that's it. So hopefully this wasn't too confusing. Always start by writing down what your original was. You can find that using your base and just the exponent. Knowing whether it's a growth or decay will let you know what shape it's going to make. Growth goes up. Then just pick out the points that you know. With our points, we know 0, 1, and 1, 3. And with also your horizontal asymptote, from there, apply the transformations to those points. Left deals with x, up and down deals with y. Now, these are probably the most confusing problems I'm going to give, so I'm going to do a couple more just to kind of help make sure that we're all on the same page. So looking at this next one, we're going to start by writing down the original. So the original function right here, my base is 1/3 and exponent x. Got it. Now, just glancing at this one, we know that this is going to be a decay. So I know it's going to start up top and swoop down. That's already part of the graph right there. Now, as far as information that we know the points 0, 1. Here, if you want, you can still do 1, comma a, or you can do -1 in the reciprocal. It's completely up to you. Just to be consistent, I'm going to do 1, comma a, and just deal with the fraction. Okay, now as far as the horizontal asymptote goes, we know that always starts with y equals 0. Now, figuring out what transformations happen, I see that I'm going to shift right by 2 because x minus 2 tells me to go right 2. So right by 2, that deals with x, and plus 5 after my function means that I will go up by 5. Up means y. I know everything that happens to this now. So applying my transformations, I see my x values are going to go right 2. So 0, go right 1, 2, right 2. For our y value, we're going to go up 5. So if I start at 1, up 5 means I will be at 6. For the next one, if I start at 1, go right 2, that gives me 3. If I'm at 1/3, if I go up 5, I'm going to be real lazy right here and just say that that's 5 and 1/3. Do I care? Nope, because I can graph that really easy as opposed to a mixed fraction. Now, for the next point, or for the asymptote, I'm usually at 0. I go up 5, so that means y equals 5. All right, we have everything we need to graph now. So graphing this, I'm going to put my asymptote at 5 right here. Got it. Now for my next point, I have 2, 6. So 2, 6 right here. And then I have 3, 5 and a third. So here is 3, 5 and a third. Well, here's 5. A third's about right there. So this one's going to swoop down this direction and then follow along the asymptote. And that's it. So knowing your transformations, you can apply them directly to individual points or an asymptote and get your graph. All right, now there's another type of transformation that's not hard to do that I want to show you. So bear with me while I give you yet another example. So starting this one off the same way that we've been doing. I'm going to put down my original. So my original one on this is 2 to the x power. My base is 2 and it's exponential, so it has that. This is going to be a growth function, so I already kind of know what it looks like. It's going to swoop up unless something special happens. And then I can put down some points. Points that I know, 0, 1, 1, comma a, which my a here is 2, and then my horizontal asymptote, y equals 0. Now, listing out my transformations, first one I see right here, I do x plus 3. So that means plus is left. So I'm going to go left by 3. That deals with the x value. The next thing I'm going to do is this negative. If I have a negative out in front of my function, that means that it's a reflection over the x-axis. Now, be very careful. I know it's very tempting to say, oh, that deals with x, but reflection over x-axis, that would take this 6 to negative 6. So I change from here down to here. That's a change in y. So I take a positive y value and make it negative. Or a negative y value, say negative 4, I reflect it, it becomes positive 4. That's a change in y. Be very careful about that. So transforming my points, I see that I'm going to go left by 3. So if I start at 0, -1, -2, -3. As far as the y value goes, I would change from positive 1 to negative 1. I flip over the x-axis. Right here, for my next one, go left by 3. That's going to give me -2. And then I will have -2 right there. Okay, now for the horizontal asymptote, well, I would need to reflect it. Well, the reflection of 0 is 0. So everything stayed the same right there. Now I can go through and graph this sucker. And you have to be a little careful about this too. Starting with stuff we know, I can put my asymptote right here. Putting a point down, I have -3, -1. So -3, -1. And then -2, -2. Right here. Now, looking at this one, it looks like I go from here to here. So these points should get lower. That's what's going to happen. Because remember, for a growth, I start low and then I swoop up. When I reflect it, I'll start low and swoop down. You have to flip it over. So this one's going to look like this. Now, is it super accurate? No, I'm not sure where it's going to cross, but we at least have the general shape down. All right, so hopefully I didn't bore you to tears on these. Okay, now the last thing on this page we're going to do, it's kind of leaving all the transformation stuff behind, is we're going to talk about a number that's very special. Now, at this point in our math career, we should all be very familiar and very comfortable with the number pi. It's used as the Greek letter, and it's 3.14, blah, blah, blah. It goes on forever, never repeats. Well, there is another number, well, actually, there's a lot of numbers like that. One special one is e. This is Euler's number, and that one is approximately 2.71, blah, 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 blah. And the way we get this is using exponentials. Now, we're not going to go through the detailed explanation of this, but just know that the exponential is what gives rise to this number. What you need to know is e is a number for us now. And it is approximately 2.71 going on forever, just like pi. Now, good news is most calculators include e in there. So if you have a TI like this one, the number e is right here above the division sign. You would press second, divide, and you would get the little e right there. Now, if you want to do it as an exponential, e to the x power, you do second ln, which is special. I'll talk about that later. That one gives you one that has an exponent already on it, but it's built into most calculators. All right, let's continue. And there's only 2 pages left. Now, I kind of took advantage of thinking you should know most of these exponent properties based on your previous classes, but just in case you don't know them or you don't remember them, I put in all the exponent laws that you need for this class. So these are the names of all the rules. You don't have to have them memorized name-wise because I don't even memorize them, but you need to know the rules. So each one of these is an exponent law that will always be true. And just because I'm a nice person, I gave you examples of how each one looks if you actually have it with numbers. So each one of these you should have seen in previous classes by this point, know them well, and then if you ever need an example, look right here and I show you exactly what it looks like. All right, now these are very useful for manipulating exponents, so you can use them to help simplify or solve equations. Okay, so all we're going to do for the rest of the lecture is work on solving exponential equations. And these aren't the only type of exponential equation that you'll run into, but they're the most common ones that you will see right now. All right, so to start with, I give you how to solve for them. And it's based on a single property that's kind of one of those, well, duh type moments, but it's super powerful. If you have an exponential that equals another exponential, and the bases are the exact same, that means that the exponents have to be the exact same. So a little example of this before we actually go on a little further, if I were to tell you 2 to the blank power equals 2 to the 5th power, equal means same, what has to be right here to make that match? It has to be a 5. Well, imagine I told you x. Still the same thing. The bases are the same. That means x has to equal 5. That's it. So if the bases are the same, ignore them and set the exponents equal. And that's the gist of a lot of these problems. But there's extra stuff to do, obviously. So take a look at this first one. Right here, I always start, are the bases the same? In this case, yes. I have base 5 equals base 5. That means all I have to do is say 2x equals negative 6 because the bases are already the same. Now divide both sides by the 2 and we get x equals negative 3. And that's it. That's the answer. If the bases are the same, set the exponents equal to each other. Okay, now another example just like that. I have an exponential equals another exponential. Base 2 equals base 2. So since the bases are the exact same, I can ignore them and just say that this is 2x plus 3 equals 5x plus 9, because the exponents have to be the same. Well, solving this, I can subtract the 5. So subtract the 5x over, that gives me negative 3x. I can subtract the 3 over, that's going to give me 6. Divide by the negative 3, and I get x equals negative 2. And we're done. So the bases are the same, set the exponents equal to each other and solve. Now, that's all nice and dandy if the bases are the same. But looking at our next two problems, these bases are not the same. I have base 2 and base 32. Well, there is a way to take care of this. The way we handle problems like this is we check to see, can I rewrite 32 so that it's 2 to a power? Now, if you already know how to do this, that's great. But it's not the easiest thing to do. So there's different ways you can go about it. You can list it out on paper, or you can use your calculator to help you out. For this one, I'll show you how you can do it on paper, but for everything else, it's going to be purely on the calculator because some of them are a little ridiculous. So looking at 32, I know 32 is 2 times 16. Well, 16 is 2 times 8. 8 is 2 times 4, and 4 is 2 times 2. So I know that my factors here, 1, 2, 3, 4, 5, there are 5 2's. That means 32 is 2 to the 5th power. All I had to do was do a factor tree, and I could divide it by 2 every single time. That's it. That's how you can do it on paper. But some numbers are ridiculous, and they're not very friendly to work with. But if you don't have a calculator, this is what you can do. Now, if you do have a calculator, here's what you need to do. Well, calculator as far as one that has y equals in graphing situation. I want to change this to base 2. So I will go to y equals. I will put 2, that's my base, and then I'll raise it to the x power. I just made this an exponential. Go to your table. What I'm looking for is 32. That happens right here. So I know 2 to the power equals 32 if the exponent is 5. This is the fastest way to do it, and if you have access to a calculator like this, your life is a lot easier. If not, you would need to use this property or this method right here. But you have 2 different ways to do it, so have at it. So I know that this is going to be 2 to the 5th power. So writing this down on the side, I know 32 is 2 to the 5th. That's important because now I can rewrite my problem 2 to the 3x minus 1 equals 2 to the 5th. Now they have the same exact base, so I can ignore the base and set the exponents equal. Okay, now I'll add the 1, divide by the 3, and I get x equals 2. Done. So first thing you should always do they have the same base? If yes, proceed about business as usual. If no, can I change the bigger number to have the same base as the smaller number? I change 32 to have the same base as 2. Always take that order first. And if that doesn't work, I'm going to show you what to do after that. But one more problem just like this one. So right here, I can do the factor tree method to see if I can change 1024 into base 4, or the calculator is a little bit easier to do right here. So I'm going to go right here. I want base 4, so I'll put 4 to the x power. I see 1024 shows up when my exponent is 5. So 1024 equals 4 to the 5th power. All right, we know what to do from here. This is 4 to the 3x plus 4 equals 4 to the 5th power. They have the same base, so I can look at the exponents, subtract the 4, I have 3x equals 1, divide by the 3, and I have x equals 1/3. That's it. That's all you got to do. All right, so we've seen what to do if the bases are the same. If the bases aren't the same, we know the first step to take. But based on context clues, that's not the only thing that you can do. All right, so take a look at these next ones. So A and B both deal with fractions. Now, I can already tell that I have base 4 and then 16. So I'm going to need to see, is there a way I can change 16 into 4? Now, hopefully you can just kind of look at this and say, oh, 16 is 4 to the 2nd power. But if you're not at that point where you can just look at it and see, we can still use our same trick. So coming over here, I have 4 to the x power. Looking right there, 16 means my exponent needs to be 2. But there is a little bit of a catch. That's 16 in the denominator. So writing this out again, have 1 over 16. That's going to be 1 over 4 to the 2nd power. That's still in the denominator. Now, is that where I need it? No. This property only works if I have base 4 equals base 4. This is base 1/4. But we have an exponent property. If I have, I'll flip back and show you real quick. If you have a fraction with a positive exponent, you can rewrite it as a negative exponent. So if I have 1 over 3 to the 2nd power, that's the same thing as 3 to the negative 2 power. Applying that right here, this is 4 to the negative 2 power. Now they are both base 4. So rewriting it, I have 4 to the 2x minus 5 equals 4 to the negative 2. They're base 2, so that gives me 2x minus 5 equals negative 2. I'll add the 5 over. I have 2x equals 3. And now I can divide both sides by the 2, and that gives me x equals 3 over 2. So in this case, don't let the fact that it's a fraction throw you. We can change it from a fraction to a whole number or a regular number by just making it a negative exponent. That's it. That's how you do it. So going through one more time, just in case you need to see another example just like that, I'm going to start with 1 over 3,125. I want it to be base 5. So what I'm going to do is I'm going to change this to be 5. Looking at this, I have 3,125 right here. That means I need exponent 5. So this is 1 over 5 to the 5th. Now to change that out of a fraction, this is going to be 5 to the negative 5th power. Got it. We know what to do now. So rewriting it, I have 5 to the negative, or to the 2x minus 3 equals 5 to the negative 5 power. Okay, they have the same base, so I have 2x minus 3 equals negative 5. Add the 3 over, I have 2x equals negative 2. Divide by the 2, and I get negative 1. That's it. That is the answer. So hopefully seeing the fractions won't be anything too crazy for you. All right, now I'm going to take what we just did and kind of bump it up just a little. Not much, but enough to be different. Okay, so looking at these, I see that I have base 3 and base 27. We know what to do here. I need to see, can I change 27 to be something that's base 3? Answer is yes. 3 times 3 is 9, times 3 is 27. So without even having to use the calculator, I know 27 is equal to 3 to the 3rd power. And if you didn't see that, you can use your calculator. There's no problem with that. Okay, well, rewriting these now, I have 3 to the 2x minus 1 power equals, this is where you have to be careful. These problems are different from the previous ones in that this one already had an exponent. So since it already had an exponent, I'm going to have to write this a different way. This has to be parentheses 3 to the 3rd, because that's what 27 is equal to. But now it has another exponent on it. Well, we know how to do this. This is another exponent property. If you have an exponent on top of another exponent, you multiply them together. So this, ignoring the bases now since they're the same, I have 2x minus 1 equals, ignoring the base, these have to be multiplied together, so I'm going to say that it's 3 times x plus 3. Multiply the 2 together. Now, if it helps, you can cover up the 3, and you can see that it's 3 parentheses x plus 3. 3 parentheses x plus 3. All right, now all I got to do from this point is solve an algebra 1 problem. I distribute my 3, so that's 3x plus 9. I can subtract the 3 over. That gives me negative x equals, add that, gives me 10. Divide by the negative, I get x equals negative 10. All done. So the new thing that got introduced here, if you have an exponent on top of another exponent, you multiply them. Now, if it's something longer like x plus 3, you have to make sure you do parentheses so that you can distribute properly. If it helps, cover up the base and you can read it exactly as is. 3 parentheses x plus 3. All right, so if you're already good after that one, go on to E. If not, I'm going to show you another. So right here, we have base 6 and base 216. I'll be honest, I can't quite remember this one. I think I know it, but I'm going to double check. So I'll do 6 to the x power. Yep, it's the one I thought it was, but best to always double check. So 6 to the third power gives us 216. 216 equals 6 to the third. All right, writing this down again, this is going to be 6 to the x minus 4 equals, parentheses, 6 to the third times x minus 3. All right, they have the same exact base now, so I can say x minus 4 equals 3 times x minus 3. Distributing, I have x minus 4 equals 3x minus 9. Move that over, that gives me negative 2x. Move that one over, that's going to give me negative 5. Divide, and we get x equals 5 over 2. That's it. That's how you do it. All right, so we've seen what to do with fractions. We've seen what to do if you have an exponent on top of another exponent. Now, let's go a little further. Got one more thing to show you before I give you something a little more interesting. Take a look at E and F. For these two, I have two different bases again. Now, the natural thing to do is to say, hey, can I change the bigger number into the smaller one? That's what we've been doing. And that's the first step I would like you to do. They don't have the same base. Can I change the big one to be the small one? So I'm going to check right here. Base 4. 8 does not show up on that list anywhere. So since 8 doesn't show up on the list, we have to be a little bit more creative right here. What we're going to do is we're going to check to see, is there a number I can change both of them into so that they have the same base? Now, my tip for this one, and listen closely, look to see if there is a number that can divide both. So the smallest number I see that can divide both of these is 2. That is what I'm going to try for my base. So right here, I'll change that to base 2. Now I'm going to look. 4 shows up and 8 shows up. So I can change both of them to be base 2. So I know 4 is equal to 2 to the second power, and 8 is 2 to the third power. Now I know exactly what to do. I'm going to replace this 4 with 2 to the second power. So that's 2 squared with 2x minus 1 on the outside equals 2 cubed with x plus 3 on the outside. That is exactly like what we did on the previous problem. We just had to add in something extra right here. Now, going through as we know how to do, that's 2 times x minus 1 equals 3 times x plus 3. Distributing, this is 4x minus 2 equals 3x plus 9. I did that almost 3 times in a row. All right, solving, I'll subtract the 3. That gives me x. I will add the 2. That gives me 11. And we're done. Nothing else to do. So my tip right here is look for a number that can divide both. All right. Now, checking out this next one, I see 125 and 625. They don't have the same base. Can I change the small one into the big one? Well, if I square this, that's going to be way bigger than 625. That turns into, I think, a 5-digit number. So I'm not going to be able to change 125 into it. But if you want to double check, go for it. That's what I like to see. But I already know I can't do it. So I'm going to try something else. A number that's small that can divide both of them, I know I can use 5. 5 divides both of those. So let's see if I can change it to base 5. There we go. 125 and 625. So I know now that 125 is equal to 5 to the third power, and 625 is equal to 5 to the fourth power. Now the problem is exactly like the one that we just did. So doing this next one, I have 5 to the third to the x minus 4, and 5 to the fourth to the x minus 3. Now I have 3 times x minus 4 equals 4 times x minus 3. Distributing, 3x minus 12 equals 4x minus 12. Coming over here, that's going to give me negative x equals 0. Divide by the 0, or not by the 0, by the negative, sorry. And I get x equals 0. So if they don't have the same base, see if you can change the small one into the big one. If it doesn't work, then see if there's a number that can divide both. Okay, moving on to the next one. Right here, I have 4 and 64. 4 is small, so I might be able to change 4 into 64. Spoiler alert, we can. But just to kind of make sure we're all on the same page, I'll put 4. 64 is right there. So I know 64 is equal to 4 to the third power. Writing these down again, I have 4 to the x squared plus 8 equals 4 to the third times 2x up top. They have the same base, so now I have x squared plus 8 equals 3 times 2x. That gives me x squared plus 8 equals 6x. Well, this looks like something I can use the ABC method on. I have x squared, x, and no x, so I'll move the 6x over. That's a quadratic, so figuring out what I can use, let's see here. Factors of this, I have 2 and 4. If I make it negative 2 and negative 4, that gives me negative 6. So x minus 2, x minus 4. And if you still prefer to do the ABC chart on the side, go for it. There's nothing wrong with getting your answer correct. So 4 and 2. This one had 2 answers, but that's perfectly fine because I wind up with x squared in the numerator. Or not numerator, I'm sorry, exponent. Done. So almost all of these have used very similar techniques every single time. Now, for this last one, I'm going to try to blow your mind a little bit. So just stick with me. It's nothing too crazy, but this is where a lot of those exponent properties are going to come into play big time. Now to start with, I want everything to be base e. E's a number, so that's perfectly fine. But looking at this, I have base e on the left side. This one looks great. There's nothing that needs to happen. Over here, I have base e right there, so that looks pretty good. But this is a fraction. I don't want a fraction. But I know how to change this fraction into a number that's not a fraction. So rewriting this, this is e to the 2x minus 1 equals, to change this out of a fraction, this becomes e to the negative 3x. Now, looking at this next one, I have an exponent on top of another exponent. That means I multiply those together. So that's e to the negative 4x. Okay. Now, using another property that we have listed on the previous page, if I have the same base times the same base, I add the exponents right here. Same base times same base, add the exponents. So doing that for this one, this will be e to the 2x minus 1 equals e to the 3x minus 4x plus a negative. That gives us e to the 2x minus 1 equals e to the negative 7x. Now they are both base e. That gives me 2x minus 1 equals 7x. Moving stuff around, I can move this one over. Doing that, it's going to give me negative 9, which I'm just going to write over here. And then equals negative 1. Divide, and I get 1 over 9. This one might look a little funny because I changed the order, but it's the right answer. All right, that's it. That's how you can solve not almost all. That's why you can solve a lot of exponential equations. There will be some more that we will need to solve, but it will require a different type of technique. Those arise whenever we cannot find a common base like this. So just be on the alert. Sometimes you can't always find the same base, but if you can, your life's way easier. All right, that's it for this lecture. If you have any questions, please feel free to contact me. I'm always happy to help out. Other than that, have a great rest of your day.